Hello everyone, welcome back to another video of NL Maths. Today we've got a second order differential equation, x double dot, which means that, let me just write here, x dot equals dx by dt. So it's the time derivative, so the second time derivative, x dot dot equals the second time derivative. So that's what it means. So x double dot plus 3x dot plus 2x equals 0. And we are going to solve this with an ansatz. And then this is really a build-up episode for another lecture, which we're going to talk about diagonalisation and solving n-order differential equations. So guessing in maths, there's a very special name actually. It's called making an ansatz. And of course, I'm going to guess that this is equal to, because look, even if you take these to the side, so x double dot equals negative 2x plus 3x dot, is like no matter how many derivatives you take, there's still an x to it. So what function, if you take the derivative many times, will have the same x and maybe plus a constant or something? Well, I'm going to guess perhaps x of t equals e to the lambda t. So maybe something like that, because if you take the derivative of e, it's going to be lambda times e to the lambda t. So since this differential equation, we're going to derive these, the first and second derivative. And if you do this one, it'll be lambda times e to lambda t, because lambda is the constant, because we're deriving with time. And then the second derivative would be lambda squared, because you're taking the lambda down here again, and you multiply it by e to lambda t again. So lambda squared e to the lambda t. And this is all the information we need. All you have to do now is plug it back into the ordinary differential equation. So then we'll get lambda squared e to the lambda t plus 3 times lambda e to the lambda t. And I don't need to put brackets here because it's multiplication, it's commutative. And then finally plus 2 times x of t e to the lambda t. And this should equal to 0. Okay, and now all I have to do is I'm going to take e to the lambda t out because it's in all of them, and we can factorize, make it simpler, see if we can solve this equation. So that would be e to the lambda t multiplied by lambda squared, and then that's going to be plus 3 lambda. And that's going to be plus 2 times e to the lambda t. So plus 2 equals 0. Now we have two specific cases for this one. It's either e to the lambda t equals 0, or lambda squared plus 3 lambda plus 2 is equal to 0. And e to the lambda t is an exponentiating function, so the only time it equals 0 is when lambda equals negative infinity. So that's not going to be the answer. So this is the one we need, and this actually has a special name. It's called the characteristic polynomial. Characteristic polynomial, and it's very important. And you may notice that it has the same name as the characteristic polynomial with eigenvalues and eigenvectors, and you will see the match immediately later. So I'm going to write here, down here, we're going to continue. So if lambda squared plus 3 lambda plus 2 equals 0, then this is a regular quadratic, and I've done this beforehand. So this would be lambda plus 2 multiplied by lambda plus 1. And that is going to equal 0. And so these are the two, a negative 2 and negative 1 are the roots. So from this, lambda equals negative 2 or lambda equals -1. So that's very good. And then we can sub this back into our equation. So that means x of t should be equal, and our guess was e to lambda t, and we have the two lambdas, but we also need to multiply it by a constant, because sometimes by differentiation you lose the constant, so we should add that constant back. C1 e to the lambda t plus C2 e to the lambda t. So that should be our answer. Actually, I'm sorry. The lambda should be lambda 1 and lambda 2. So if we're referring back to this one, this would be lambda 1, lambda 2. So it's easier to refer to later. So then we need to find the constants, but let's just sub in lambda first. So lambda 1 was equal to -2. And C2 was equal, lambda 2 is equal to -1. So, but the thing is, I haven't specified something really important, is that whenever you have any dimension of a differential equation, you need initial conditions. And how many? Well, it depends on the dimension of the equation. So what do I mean by the dimension? Is how much information do you need? Well, we need x and x dot. Once we know the two, x double dot is just the derivative of x dot. So we only need these two. So this is a 2D problem. So then, if it's a 2D problem, we need two sets of information. So we need x of 0 and maybe x dot of 0. So the derivative. So those are the two main information we need. So we need x of 0 and x dot of 0. And in the equation, it's going to be 2. And this is going to be equal to -3. So this is going to be very easy for us, because if it was other equations, it would be hard. So to determine these C1s and C2s, and we'll see for higher order differential equations as well, we need these initial conditions to help us determine them. So let me look at x naught first. So when t equals 0, when t equals 0, e to the power of 0 is always 1. So that's going to be C1 plus C2, because this is always 1, this is 1, so C1 plus C2. And then we have x dot of 0, but I'm going to compute x dot first. X dot is going to be C1, and then you bring the lambda down, C1 lambda times e to lambda t times e to lambda t, lambda 1, plus C2 lambda. Oh, I'm so sorry. Oh, wait, no, we can continue. Lambda 2 times e to lambda t. And we have lambdas and lambda 2. So that's going to be C1, and C1 is negative. So negative C1 times 2 times e to lambda t. And then minus C2 e to lambda t. Okay, so then when x dot is at 0, this is going to be equal to -2C1, because this goes to 1, minus C2. And we have a simultaneous. Now, I'm not going to bother your time with simple algebra, so I have solved this, and we will see that. And this is why I picked these two initial conditions. These are very easy to solve. You can try doing the simultaneous yourself for practice. C1 equals C2 equals 1. That's the answer to the simultaneous. Therefore, x of t equals, and from our above form, since C1 and C2 are both 1, we can cancel them out. So the answer to our differential equation would be e to -2t plus e to -t. Now, what I forgot to mention actually was something very important. I'm very sorry. Is that why are we adding two e's? Because from our Ansatz, the answer is e to lambda t, not e to the lambda t plus e to lambda t. And this is because of the superposition principle. So the superposition principle states that for any linear system, a linear system is like a straight line, something that does not include sines, cosines, or anything to the power of, which is exactly what we see here, no powers, just coefficients. Then that means all the answers to the differential equation can be, or the linear system can be added together, and that would still hold to be a solution to the equation. So it's like when two waves add up, you can have a bigger amplitude, and that's the superposition principle. So that's why we can add the two up. Okay, so that's good. Now I've got one last thing to show you, which is very cool, and this leads on to our next lecture's topic. So if we were to plot this on Python or something, or even anything really, plot it on any computer software, we want matrices, because we want them to be a first order differential equation. Because the first order differential equations, they're very easy to solve, and we'll look at that in the next lecture actually. So what we want, we'll have, and remember what I said about the 2D system, we only need two pieces of information. We'll have x and v in a matrix, and we'll actually d by dt it, and v is going to be equal to x dot. So when we take this into the computer does not need to deal with the derivative of x, so it's going to be x double dot and all of that, because we've got x and v. So this is very simple for the computer to do, a first order differential equation. And now it's going to be a matrix multiplied by x of v, because this is going to be x dot and v dot. So we're going to look back to our original equation. I'll write it down here. X double dot plus 3x dot plus 2x equals 0. And this was our original equation. And now how are we going to do this? Well, x dot is, so this x dot is going to equal to 0 x's and 1 v, because x dot equals v. Look, x dot equals v. So then this is 0 of x and 1 of v. That's how I think of it. So this is like the x and v when you multiply it. So like x dot equals 0 of x's and 1 v, which is x dot, really. And the next one, which is going to be v dot, what is v dot equal? Well, that's x double dot, really. And we can change this equation into x double dot equals negative 2x minus 3x dot. So then if you flip this around, x is equal to negative 2, and v, which is x dot, is equal to negative 3. So that is very good, because we've simplified a second order differential equation into one first order with 1 d by dt, and it is easier for the computer to solve. We're using matrices, which is much easier for the computer. I wanted to show you one last thing before I ended today's video, which is, do you remember the characteristic equation from previous to find the eigenvalues and eigenvectors? Well, from the previous lecture of eigenvalues and eigenvectors, that was the determinant of a particular matrix A minus lambda I is going to equal 0, where lambda is the eigenvalue. Now this is very good, because let's say we can name this matrix A, and if we solve the eigenvalue of this particular matrix A, which we will do right now, then we will get 0, 1, negative 2, negative 3, minus lambda 0, 0 lambda. And this is going to be equal to negative lambda 1, negative 2, negative 3 minus lambda. And if we take the determinant of this, so negative lambda times negative 3 minus lambda, and then minus 1 times negative 2, so let's quickly complete this. This is negative lambda times negative 3, which is 3 lambda, minus lambda squared, plus 3, and then let me just rearrange this. Negative lambda squared plus 3 lambda. Oh, sorry, this is plus lambda squared. Plus lambda squared plus 3 lambda plus 3 equals 0. That is the characteristic polynomial that we saw from the very start, this characteristic polynomial. And this is exactly what we get when we do the eigenvalue equation. So we can see that there is a relationship between the eigenvalue and the characteristic polynomial to determine the roots of the differential equation. So we are going to be using this fact in the future lectures for diagonalisation to make matrices, these first order ones for n order derivatives, and we'll be using this to make it much easier for the computer to solve. And that's what's so great about eigenvalues and eigenvectors, and we can see this through this 2D linear differential equation. Okay, so that's it for me today. Thank you very much.